Hello friends. So today we are going to solve the questions from modern physics. And these questions are from the year 2023. And total question we are going to try to solve are 5. And all these questions are from the mains. And for the year 2023, this is part 2. The first part also, we solved I think around about 10 or 11 questions from the year 2023. So the first question, it states that the energy density associated with electric field E and magnetic field B of an EM wave in free space is given by, where this epsilon naught is permittivity of the free space and mu naught is permeability of the free space. So this question is, you can say, directly based on the formula itself. So we know that the standard formula for our electric field we can say for electric field, if that is given as U of E, then U of E is equal to half epsilon naught E square. And next is our magnetic field. And if that is given as U of B, then our U of B will be equal to half B square upon mu naught. Okay. So it is half epsilon naught E square, and option number D is the correct one. Option D is correct. Next question. It states that the amplitude of magnetic field in an EM wave propagating along y-axis is 6.0 into 10 to the power minus 7 Tesla. Maximum value of electric field in the electromagnetic wave is. Maximum you can say amplitude of magnetic field is given, and we are going to find out the maximum value of the maximum amplitude of electric field. So we know that our maximum amplitude of electric field is equal to C times the maximum amplitude of the magnetic field. Okay. And we simply substitute the values. C is our 3 into 10 to the power 8, and magnetic field is given as 6 into 10 to the power minus 7. So this we are going to get as 180 volt per meter. So this will be our maximum amplitude. Option 2 is correct. Next question. It states that a plane EM wave of frequency 20 MHz propagates in free space along x direction at a particular space and time, E is 6.6 J unit vector volt per meter. What is B at that point? Okay, so we have to find out its magnitude as well as the direction. And we are given that electric field is along our J unit vector, or we can say along y-axis. So we can say our electric field is along y direction, and the wave is propagating along x-axis, x direction. So we can say wave is propagating along x-axis, x direction, and we know that our electric field is always perpendicular to the magnetic field, is always perpendicular to the direction of propagation. Direction of propagation. These three are always perpendicular with respect to each other. So it means our magnetic field B will be perpendicular to our E is given in J unit direction, and our magnetic field is also perpendicular to our I unit vector, okay, along x-axis. So it means we can just and we can also draw an important conclusion from here, that our E cross B it should be along x direction. X direction. X direction means the in which it is propagating. Okay. Therefore, we can say that our electric field is along our J unit vector, and magnetic field, let us suppose we call this as B unit vector, and their cross product should be giving us a x direction, that is a y unit vector. Therefore, from here we can say that our B unit vector should be our plus k, or we can say z direction. Direction we found out. Now we can simply use our for the magnitude. So we can say magnitude, and we know that our magnetic field is equal to electric field oblique speed of light, and this is for free space, and both the values are given to us, or we are known to it, 6.6 3 into 10 raised power 8. So we get here 2.2 into 10 to the power minus 8 Tesla. Therefore, we can write that our magnetic field is equal to 2.2 into 10 to the power minus 8, and we have this as k unit vector Tesla. So we have 2.2 minus k unit vector. Option 2 is correct. Next question. It states that which of the following Maxwell equations is valid for time varying condition but not valid for static condition? Okay, so these are the standard formulas. So let us discuss all these formulas one by one. So we start with the option 1. Option 1 is our closed integral of our b dot dl is equal to mu naught I, and this is our nothing but our Ampere's law. And this Ampere law is valid only for static or steady state condition. So this you can say valid for static or steady state current, steady current. And not valid it is not valid for time varying condition. Time varying conditions. So this option is incorrect, and let's try our option number 2, which states that our integral, closed integral of our electric field dot dl is equal to 0, and this is our Faraday's law in electrostatic. It is called as a Faraday's law, and this law is valid in only static condition. Valid only in static condition. And not valid for our time varying. Not valid for time varying. Time varying basically we can write not valid for time varying when its partial derivative upon dt is not equal to 0. And we come to the option 3, which gives us that closed interval E dot dl is equal to minus partial derivative of the flux and the time. And this, okay, here I forgot to mention, this is Faraday's law in electrostatic. And this is also Faraday's law, but is for our electromagnetic induction. Faraday's law for electromagnetic induction. And this is, you can say, specifically is for, we can rather put it in words, that this equation specifically arises due to time varying magnetic field. This equation specifically arises due to time varying magnetic fields. And it does not hold for our static condition. Valid for static. So therefore this option 3 is correct. 2 is also incorrect. And we can also discuss option number 4. Option 4, and it gives us that for closed integral our d is equal to 0, and this is our nothing but Gauss law. For electric fields. And this is true for both static and dynamic. Valid for static and dynamic conditions. So therefore option 4 is also incorrect. So only option 3 is correct. Three is correct. Next question. It states that in an EM wave at an instant and at a particular position, electric field is along negative z axis and magnetic field is along positive x axis. The direction of propagation of the EM wave is. So here we are going to find out the direction of the propagation, and we are given that of electric field it is along negative z axis, or we can say minus k unit vector, and we are given that our magnetic field is along positive x-axis, which basically means plus I unit vector, and we have to find out the direction of propagation. And we know that our electric field is perpendicular to the magnetic field is perpendicular to direction of propagation. Or we can also say in other words that the cross product of our electric field and magnetic field will be giving us direction of propagation. So let us substitute their unit vectors. Electric field, we have our minus k unit vector cross, and this is a plus I unit vector, and direction of propagation let us represent as our n unit vector. So from here we get that our n unit vector will be equal to our minus of j unit vector. So the direction will be our option number 2, that is negative y-axis. So you can say direction of propagation will be equal to negative y-axis. Option 2 is correct.